You ever wonder how an AI actually learns? The one in your phone that recognizes your face, or the one that translates a sentence in a split second. It really does feel like magic. But the blueprint, the core idea for how most modern AI works, can be traced back to a single revolutionary paper from way back in 1986. So today, we're going to unpack that paper and get to the bottom of the elegant concept that taught machines how to learn from their own mistakes.
Okay, so let's really think about this for a second. Picture a modern AI. It's got not just thousands, but millions, sometimes billions of tiny digital connections all firing at once. And when it gets an answer wrong, let's say it sees a picture of a cat and calls it a dog, how in the world does it know which of those millions of connections to tweak, and by how much? That right there, that's the fundamental puzzle we're going to solve today.
Well, the key that unlocked this whole puzzle was laid out in a landmark 1986 paper by three researchers, David Rumelhart, Jeffrey Hinton, and Ronald Williams. What they came up with was a learning procedure that would become the engine of the entire deep learning revolution that we're living through right now. And here it is. This is the paper itself, published in the journal Nature. And yeah, it looks pretty dense and academic, right? But inside this text is a mathematical and conceptual framework that was, for its time, just breathtakingly clever. It finally gave researchers a practical way to train these complex artificial neural networks, something that had been a massive roadblock for decades. So what was this giant roadblock they managed to bulldoze? Well, it all centered on something deep inside the network that researchers couldn't directly see or control. It was a part of the network they called the hidden layer. So take a look at this diagram. It's pulled right from the paper. You've got your input units on one side, that's where the data comes in, and you've got your output units on the other. That's where the network spits out its answer. But sitting in between are these mysterious hidden units. They do all the heavy lifting, the really complex processing, but because you can't see what they're doing, figuring out how to train them was this huge, huge challenge. And this gets us right to the heart of the issue, which has a formal name, the credit assignment problem. Look, imagine you're the manager of a huge company, and a final product comes off the line with a defect. You know the final assembly team messed up the last step, but the real error could have started anywhere, maybe in design, or manufacturing, or quality control. How do you trace that error all the way back and assign just the right amount of blame to the right department so they can actually fix it? That's the exact same problem AI researchers were staring down. So here's the bottom line. It's super easy to know if the network is wrong. I mean, the network gets dog, but the picture was clearly a cat. That's a simple comparison. But figuring out why, pinpointing which of the thousands of internal connections led to that mistake and how to fix them, that was the puzzle that had the entire field stumped for years. And this is where the 1986 paper delivered its absolute masterstroke. It laid out an elegant, mathematically beautiful method for solving that credit assignment problem, finally allowing the network to effectively learn from its own mistakes. They called it backpropagation. It's such a simple name for a profoundly powerful idea. And, the name itself gives you a pretty big clue as to how it works. Instead of just moving forward from input to output, they found a clever way to send information, specifically information about the mistake, backward through the network. Let's break it down real simple. First, the network gets an input, like a picture, and it makes a guess. That's the forward pass. Second, you compare that guess to the right answer and you measure how wrong it was. That's your error. Third, and this is the magic part, you take that error number and you send it backward from the output layer to the hidden layers. It's like each connection gets a little whisper telling it exactly how much it contributed to the total mistake. That's the backward pass. And finally, based on that whisper, each connection adjusts its strength just a tiny, tiny bit to do better next time. And then you just repeat that loop, thousands, millions, even billions of times. So really, it's just a brilliant, systematic way of passing the blame backward. The output layer knows exactly how wrong it was. So it turns to the layer right before it and says, hey, you contributed this much to my screw up. Then that layer turns around and tells the layer before it how much it contributed, and so on, all the way back to the very beginning. It's a chain of accountability that allows the entire massive network to learn together. Now, having a great algorithm is one thing, but you've got to prove it actually works. And the experiment that researchers came up with was, honestly, just as elegant as the algorithm itself. They didn't just want to teach the network to recognize simple patterns, they wanted to see if it could learn abstract human concepts. So what they did was they fed the network information from two different but intertwined family trees, one English and one Italian.
They gave it simple facts, things like Christopher's father is Andrew, or Gina's husband is Emilio. And the network's job was to take a person and a relationship, like Penelope and mother of, and then spit out the correct person's name.
But here is the crucial part. The goal wasn't just to test the network's memory. I mean, anyone can memorize a family tree, right? The real question, the big what if, was could those hidden units, that mysterious middle layer, start to build their own understanding of the data? Could this thing actually discover concepts all by itself?
And the result, which you can see right here in the analysis from the paper, was absolutely astonishing. When they peeked inside the network's brain after all that training, they found it had spontaneously organized people based on properties it was never, ever taught. For instance, one of the hidden units basically figured out how to separate the English family members from the Italian ones. Another one learned to separate them by what generation they belonged to. This was the home run. This was the proof. The machine hadn't just memorized facts, it had learned abstract relationships. It had built its own internal model of the world it was shown. This proved that backpropagation wasn't just some clever math trick. It was a genuine way for a machine to build its own complex understanding, its own representations of data. And that is the foundation of everything we call deep learning today. But, of course, like any truly great scientific paper, the authors were also incredibly honest about the limitations of their work, even as they were literally laying the groundwork for a revolution. I mean, the impact is undeniable. Backpropagation is still the core algorithm used to train the vast majority of AI models today. But the authors themselves pointed out some big limitations. First, they said, this is probably not how our actual biological brains learn. And that's a big deal, because the human brain is incredibly efficient. So if we could figure out how it learns, we could probably build much less power-hungry AI. Second, they noted the algorithm can sometimes get stuck. Think of it like you're hiking in the mountains and you find the bottom of a small valley. It's a low point, sure, but the deepest valley might be just over the next ridge. The algorithm can find a pretty good solution, but not always the absolute best one. I just want to pause on this date for a second. 1986. This was happening before the World Wide Web was even a public thing. The most powerful supercomputers back then had less processing power than the smartphone you're probably holding right now. The ideas in this paper were so far ahead of their time, so far ahead of the hardware, that their true potential wouldn't even begin to be unlocked for another 25 years. And this final quote is just amazing. Now, gradient descent is just the fancy mathematical term for that whole process we talked about, of gently nudging all the network's connections, bit by bit, to reduce the error. And even in their moment of absolute triumph, the authors wrote this. They acknowledged their model wasn't a perfect copy of the brain and basically challenged the world to keep searching for even better, more brain-like ways to learn. They weren't just inventors, they were true pioneers, charting a course for generations of researchers to come. So, backpropagation gave us this incredibly powerful way for a machine to learn from its mistakes by systematically assigning blame. It's what turned AI from a cool theoretical idea into a practical engineering powerhouse. But it leaves us with this one fascinating final thought. If this is the algorithm that allows machines to learn and discover things for themselves, what happens when they use that variability to discover a learning algorithm that's far better than this one? What's the next great leap forward? That is the incredible question this paper from 1986 still asks us today.